In this video, we'll use figures and animations to better understand Riemann sum and definite integral. How can we find the area under a smooth curve between A and B? Riemann sum breaks the area into a finite number of rectangles. For example, here we set n equals 10, meaning we use 10 rectangles to approximate the area. Three common types of Riemann sums: left endpoint, right endpoint, midpoint. Each method uses equally partitioned subinterval. As we increase the number of rectangles, n grows. Each rectangle becomes narrower. With thinner rectangles, the approximation fits the curve more accurately. In the limit as n approaches infinity, the Riemann sum converges to the definite integral. The discrete delta x becomes the infinitesimal dx. The summation symbol, sigma, becomes the integral sign. Now let's visualize the three main types of Riemann sums. Here we use a simple quadratic function as a given function. In the interval a to b, the partition number n equals 10, creating 10 rectangles to approximate the area. These highlighted points are sample points. For left Riemann sum, points start at A and end just before B at B minus delta x. Right Riemann sum, points start just after A at A plus delta x and end at B. For midpoint, sample points sit at the center of each subinterval. So just plus half delta x. Here, for each subplot, we draw the blue curve in the interval a to b. Then for each plot, the first one shows the area under the curve. The other three subplots are for those three common types. Let's run the code. Those three methods produce slightly different approximation, but the midpoint one is more accurate. Next, let's visualize the convergence of Riemann sum to the definite integral by Python. Here we kept the partition number at n equals 100, because after that, the approximated area already looks pretty much the same as the actual area. We use midpoint Riemann sum for our animation. Let's run the Python code. As n grows, more rectangles, the total area gets closer to the actual area. As n approaches infinity, the Riemann sum converges to the definite integral. In our example, we use the function 15 times x plus 1 squared, which is entirely above the x-axis. The area is positive because all the rectangles above x-axis. Now, suppose we modify the function, like upside down 15 to negative 15, or further shift the graph down by 100 units. So the first case, all rectangles are below x-axis. The total area is negative. And for this shifted case, the rectangles partially above and partially below the x-axis. So we have a net signed area. The definite integral represents the net signed area because the Riemann sum naturally has the sign of each rectangle height, the y value at sample points. Let's run the Python code. Here is the original function, and here is the modified one, which shifts the curve down by 100 units. Over the interval -1 to 3, two shaded regions between the curve and the x-axis. The red area above the x-axis represents a positive value. The green one below has a negative value. The total net area can be positive, negative, or 0, depending on their sizes. If the red area is larger, the total area is positive. If the green one is larger, then the total area is negative. Or if both are equal, then the total area is 0. The definite integral is 0. In the next video, we'll study on the difference between area under a single curve and the area between two curves. For the area between two curves, we always subtract the lower curve from the upper curve, so the result is always positive, representing the true geometric area between two curves. The area under a single curve is exactly what we're learning about in this video.